episode of Paralogic. So today we're gonna continue with problem 22 from where we left off. And Amelia starts on the number line at 0 and crawls in the following manner. For n is equal to 1, 2, 3, Amelia chooses a time duration t of n and increment x sub n independently and uniformly, that's an important word, and random from the interval 0, 1. So this basically means that it's going to be linear. And during the nth step of the process, Amelia moves x sub n units in the positive direction using up t sub n minutes. If the total elapsed time has exceeded 1 minute during the nth step, she stops at the end of that step. And otherwise, she continues with the next step, taking at most 3 steps in all. What is the probability that Amelia's position when she stops will be greater than 1? Alright. So now let's just analyze what we have right here. So basically, in each of the 3 times, she's gonna choose a number between 0 and 1, and also a number between 0 and 1 for both of x of n and t of n. But they are not necessarily equal. And then we're gonna use up t sub n minutes to increment our time by x sub n. So let's say one of the example, let's say if I use 0.5 to 0.5 minutes, and then I try to increment my step by 0.75. Then basically, like if I choose this, then after 1 second, my position would just basically be 0.75, and the minute that I've used is 0.5. And what if I just do again by choosing 0.65 and 0.8. Now my position will just be at 1.55, and the time that I've used is just gonna be 1.15. And let's look at when is he going to stop. So if the elapsed time has exceeded 1 minute during the nth step, she stopped at the end. So now we just see that at this point he's gonna stop, and since his position is actually greater than 1, then this is actually what we wanted, one of the case. So how are we gonna generally solve this problem, because there are just too many cases to be handled? Well, let's just look at the cases when he's gonna stop after 2 steps. Let's just remind us what the condition is, because he's gonna choose any number between the open interval 0, 1. However, the time must exceed 1 minute to stop. So therefore, it's impossible for him to stop right after he moved the first time. So therefore, the only 2 cases will just be stop after 2 steps and stop after 3 steps. So now let's just do case 1. First, stop after 2 steps. We basically have 2 times. I'm just gonna call it T1 and T2. So these 2 must actually be less than. No, these 2 must be greater than 1, because, well, after 2 steps, the total time must be greater than 1. That's one of the conditions to make it stop. But we also have x1 plus x2 must also greater than 1. So we basically have this system right here, which both x1, x2, t1, t2 are all just within the bound between 0 and 1. So how are we going to possibly do that? Now we're just gonna do a geometric probability. So let's say that, because of symmetry, we just change these variables, but they're still independent of each other. So therefore, we know that these are basically exactly the same. So now, what does it mean that both of x1 and x2 are between 0 and 1? That this means that they must lie within this square, which this will be 1 and this will be 1. And what is the graph t1 plus t2 is greater than 1? Well, now you might just try to turn it in slope-intercept form, but we can just look at what's happening. So basically, whenever the other thing is 0, then the opposite one must be 1 because we have this sum. So we just graph it. We're gonna graph like in this form, right? And because this is greater than 1, then the solution set or the area that we want will just be this shaded portion. Will just be this right triangle right here. And obviously this one, because we have a base of 1 and a height of 1, then this will just be 1 times 1 over 2, which is 2. Which is 1/2. Sorry, okay, but which is 1/2. So for each of these solutions, the probability that this will happen will just be 1/2. So the case 1 will just be simply 1/2 square, which is 1/4. Alright. Now let's go to the next case. What if we stop after 3 steps? Well, I see that it's kind of cute since it's only one number, in contrast to this large phrase, but let's just continue here. So we're gonna have t1 plus, so you might think that, well, it's just t1 plus t2 plus t3 is greater than 1, and x1 plus x2 plus x3 is greater than 1. Well, isn't it just this? So the solution set of these two equations? Well, not necessarily, because what if these two are already greater than 1? Then we probably just don't want it to happen, because once we reached because well, actually, yeah, we cannot just simply do that to system, because so we have x1 plus x2 plus x3 must be greater than 1. But yeah, you might just think that t1 plus t2 plus t3 is greater than 1. Well, just combine these two and find a solution set and done. But not necessarily, because what if we already have this sum, t1 plus t2, to be greater than 1? Then this basically means that we're gonna stop right over here, and these were just not gonna be relevant, and we're not gonna even take the third step. So therefore, we must have this one to be actually less than or equal to 1 in order for us to take the third step. So essentially, this solution set would just be, well, x1 plus x2 plus x3 is greater than 1. Well, now how are we going to express this condition right here? Well, if this one's actually true, then therefore t3, there will always gonna be possible to sum it up to greater than 1. So essentially, we can just write it as this equation, t1 plus t2 is less than or equal to 1. And that is essentially just these two equations. So now how are we going to calculate this? Well, if you do not have knowledge about linear algebra, then this might be a little bit hard for you to possibly evaluate or visualize. But the key idea to here will just be try to visualize it in terms of a 3D graph. So we're just gonna say that this axis is x, this axis is y, and this axis is z. Alright. So now what does this even mean? Well, let's just say that x1 is x, x2 is y, x raised to. Now, let's just imagine, okay, if z is equal to 0, like if there's no altitude at all, then what is the equation, or what is the graphical form? Then that will simply just be a 2D equation, a 2D graph that looks identical to this. Well, keep in mind that now we're considering the case of x1 plus x2 plus x3 is less than or equal to 1 in order to make the complementary counting. Now let's just continue. What if x is equal to 0? Then analogously we're gonna have this shape, and same as y is 0, then we're gonna have this shape. So basically, it's pretty easy to prove that at any of the point that's within this pyramid right over here, it actually satisfies this equation right over here. But keep in mind that we're doing complementary counting, so what is the range that we're actually doing? Or otherwise, like, what is the total? So basically, you can just do 1 minus the area. No, 1 minus the volume of this. So what is the 1 even representing? You might actually rise this question up. So now, 1 would just actually be the total space of points that we can choose such that of x, y, and z, such that x is less than, such that 0 is less than or equal to x is less than or equal to y, 0 is less than or equal to y is less than or equal to 1, and 0 is less than or equal to z is less than or equal to 1. So this is actually the set that we're choosing. And if we want to actually try to visualize it in the 3D plane, then that is simply just a cube, like a unit cube. That actually just encompasses all of the possible points. So now, what is the volume that is inside this cube, but outside this pyramid? That would just simply be 1 minus volume, right? And now let's just try to compute what the volume is. Volume, if you recall the volume formula of a pyramid, that would just be 1/3 times BH, that is equal to V. So now base is just simply this triangle right over here, which is just 1 times 1 over 2. And that's the base, but then we're going to multiply it by 1, but then don't forget the 1/3. That would just simply be 1/6. So now we got the volume, 1 minus volume, which is going to be 1 minus 1/6, which is equal to 5/6. Alright. So now we got this part of the solution, but what about this part? Well, this part, like if you recall it, then that's exactly same with this, right? Because this part will just be in the 2D graph, just still the same line, but except that we're actually finding the other part. Well, because this is the midline that cuts the entire square into 1/2, then there will just be 1/2 as the area. So now we just combine these two solution sets to get us. It's actually 5/6 times 1/2, which is equal to 5/12. So we have these two cases, which gives us 1/4 plus 5/12, which is equal to 3 plus 5/12. And that gives 2/3 as our final answer. Thank you for watching, hope you enjoyed, and I will see you in the next video. Goodbye. Now let's go on to number 23. Let x sub 0, x sub 1, x sub 2, ... be a sequence of numbers where each x sub k is either 0 or 1 for each positive integer, and I'll define this. So s sub n is equal to the summation from k equals 0 to n minus 1 of x sub k times 2 to the case. Now suppose 7 times s sub n is congruent to 1 mod 2 to the n. For all n is larger than or equal to 1, what is the value of this? Now first, let's just think, why are these just significant? Well, actually, there might not be any significance of these numbers, which kind of like depend on which method are you using, but let's just try to dig into this problem right now. So, well, actually, this problem is kind of hard to understand, but it's just saying that this series, this summation, well, actually, this list of coefficients actually determines that for all of the natural numbers, and then this always satisfies. So let's just do some examples. I'm just gonna make a grid. Let's just say that this value is gonna be n. So if n is equal to 1, then what satisfies 7x is congruent to 1 mod 2 to the 1. And we know that, and we also have a range of x. So x can be anywhere that is less than 0, but less than or equal to 2. And let's just see that whether this summation actually seems to be a bit familiar. Well, all of the coefficients are either 0 or 1. And does that seems to be like a bit familiar or some mind calling? Well, this is basically the binary representation of a number. So this might just hint us that there might only be one such solution for each that is uniquely determined. So now, 7x is congruent to 1 mod 2, and that is just trivially being 1. Okay, now what about 7x is congruent to 1 mod 4? And that basically means that n is equal to 2. Now, if 7x is congruent to 1 mod 4, we can just plug in Chuck, and we're gonna get that x is equal to 3. Okay, now let's go on to the next one. Let me just write this a little bit bigger for it to be easier to see. Now let's go to the next one. What if 7x is congruent to 1 mod 8, which is just consequently. So if 7x is congruent to 1 mod 8, then, well, let's just write down x equal to 3. Then x is going to be equal to 7. Now let's go on to the next one, and for the sake of simplicity, I'm just going to write 16 over here. Then if 7x is congruent to 1 mod 16, then we're going to try and it's still 7. And that's 64. Why did this change? But it did not change from here to here. Why is that? Well, let's just try to find some more patterns. Now what if this is equal to 32? Then 7x is congruent to 1 mod 32. Then after trying, we're gonna see that x is actually equal to 23. Wow, such a big jump. Let's just record what is the increment between each consecutive. 0, this plus 4, and from 3 to 1, obviously, plus 2. Okay, now let's go to the next one. Now if we get to 6, then this one will just be 64. And now let's just see what satisfies the congruence. That 7x is congruent to 1 mod 64. Now it turns out that x is actually equal to 55. And this increment is by 32. Now just try one more to see what is happening. And if you try to calculate that out, then we're gonna see that this in fact is still 55. Well, this is because 55 times 7 plus 1, no, 55 times 7 minus 1 is equal to 384, which is both a multiple of 64 and 108. And so does 7 times 7 minus 1 is 48, so it's divisible by both 8 and 16, and that is why it does not increment. Now let's look at what number is actually being incremented. 2, 4, 16, 32. These number just seems to be a bit special. Well, yes, these are actually powers of 2. And you might just wonder, well, why is that even happening? And what can we even draw from that? So basically, if we look at all the incrementing numbers, and this basically just tells us that this number is actually S5 minus S4. Because we know that S4 plus x sub 4 times 2 to the 4 is actually equal to S5. So basically this tells us that x sub 4 is actually equal to 1. But this one tells us that x sub 3 is equal to 0. And this tells us x sub 2 is equal to 1. Okay? So now let's just try to dig into the expression of this modulus deeper. Well, because we see that 2019, 2020, 2021, and 2022 are just too big of a number that we're gonna try each number and find the value. That's just going to take forever. So, well, 7s of n is congruent to 1 mod 2 to the n. Okay. Well, is it possible to try to derive something and see what are the relationship between these two. So that kind of gives us an idea about induction, because we know that this expression in fact satisfies for all natural numbers. So this can basically just act as a domino theory, or because the preceding block is gonna push down the block after, and see what's going to happen. So we know that we're gonna have 2 to the, or 7 s of n minus 1 is congruent to 1 mod 2 to the n minus 1. So 7 times s sub n minus 1. So s of n minus 1 can in fact be expressed as, or some coefficient k that is called k1 times 2 to the n minus 1 and plus 1 and divided by 7. So now that is basically an expression for s sub n minus 1. Now, how are we going to reach s sub n? So we're just gonna say that well, s sub n is actually equal to s sub n minus 1 plus x sub n times 2 to the n. So if we just substitute that expression up back in, we're gonna see that it's actually equal to k1 times 2 to the n minus 1 plus 1 over 7, and that plus x sub n times 2 to the n. Now we have finally 7 s sub n just equal to 7 times k1 2 to the n minus 1 plus 1 over 7 plus x sub n 2 to the n, which is equal to k sub 1 times 2 to the n minus 1 plus 1 and then plus 7 x sub n 2 to the n. But that is actually an expression for 7 times s sub n. Okay. So now, well, this one is actually congruent to 1 mod 2 to the n plus 1. Okay. Now if we just examine this expression a little bit, well, actually this one is congruent to 1 mod 2 to the n. So let's see. Well, we can just get rid of these. We're gonna see that k1 times 2 to the n minus 1 plus 7 x sub n 2 to the n, that is actually equal to 0 mod 2 to the n. Now let's factor this a little bit. That is equal to 2 to the n times k1 over 2 plus 7 x sub n, and we know that this part must be an natural number. So that's actually one of our conclusion. Well, because this one is congruent to 0 mod 2 to the n. Okay. actually, excuse me, here should actually be 2 to the m minus 1. Here should actually just be 2 to the m minus. No, wait, this should still be 2 to the n still. So now we can actually see, well, because we don't even know what is the value of x sub n, but we kind of know k of 1 just based on the previous inductive step. So let's just do some discussion about the parity of k1. So let's say if k1 is actually, well, what if 2 is divisible by k1? Then if 2 is divisible by k1, then x sub n must also be divisible by 2. But we actually know that in this case, x sub n is just forced to be 0. Because so x sub n is just forced to be 0. Now, what about 2 is not divisible by k0? Well, you might ask the question, why is x sub n forced to be 0? Because we're going to look back into the initial condition, and that basically just tells us that all of these are either 0 or 1, and one of them are divisible by 2 and one of them are not divisible by 2, so it must just be forced to be 0. So now, if 2 is not divisible by k1, or if 2 is not divisible by k1, then k1 is just going to be equal to 1. So we actually just derived what we have to do with k sub n. So now it just left us to determine what are the values that will cause, k sub 1 to be an odd number, and which of them are going to be caused by even number. Well, there might be a faster way to do it, but we're just going to proceed by finding some more patterns. So now we can see that 55 is actually odd, because 55 times 1 times 7 minus 1 over 64 is actually equal to 6, and 6 is an even number. And in fact, well, if we find all of the coefficients, then we're gonna get 3, 5, 6, 3, 5, 6, 3, 5, and 6 for all of these patterns. Well, and we can see that there will actually always be a change, or there'll actually be no change between 6 and 3, because 6 is an even number and 3 is an odd number. But there will always be a change, well, between 3 and 5, 5 and 6. Well, I mean, for a change, I just mean between 0 and 1. So basically, this means that we're gonna have 0 for all of the numbers . Zero for all of these. So essentially, we can see that, like, 3 is actually just this one is actually x sub 1, and this is x sub 2, and this is x sub 3. So essentially we see that it is 0 whenever x is a multiple of 3, or whenever x sub n is a multiple of 3. So x sub n is equal to 0 when n is divisible by 3, and x sub n is equal to 1 otherwise. And the specific proof will just be left as an exercise to the reader, but you're just gonna get the same result. So now let's just see these expressions. Well, 2019 is a multiple of 3. So this one will be a 0, and this one will be a 1. This one will be a 1, and this one will be 0. So the answer is just simply 2 plus 4, which gives us 6 as our answer choice A. That's a long problem. Thank you for watching, hope you enjoyed, and I will see you in the next video.